Alright, hello guys, my name is Zach Mwaldi. I'm here to teach you about Sn1 substitution. So, as the name implies, substitution is when you switch one thing with the other. So let's write the general formula for an Sn1 substitution. Alright, this is the general formula for an Sn1 substitution. You have an alkyl halide here, and then a protic solvent. By protic means that it has an alcohol group. It could also be water, where it has like a an oxygen that can make an ester with lone pairs of electrons, right? And sometimes we use AgNO3, silver nitrate, to use it. We sometimes use it as a catalyst. So the alkyl halide, the X could be fluorine, chlorine, bromine, and iodine. So, what happens here is that the halide gets kicked out, and then it's replaced with an oxygen, and it's attached R group. R could be anything, so it could be like an ethyl, methyl, whatever group, right? And you make an ester at the end. So let me draw out the mechanism, and let me explain to you how this reaction works. So the first step is the electrons that are bonded from the carbon go to the alkyl halide, or I guess the halide atom. So it could be fluorine, chlorine, bromine, or iodine, right? And it makes this intermediate that we call a carbocation. It's a carbon that's positively charged. The halide takes away the electron bonded because it's an electronegative group, so it withdraws electrons from whatever it's attached to. And the silver nitrate, it's sometimes used, sometimes not. You don't really need it for the reaction, but helps with the reaction. What it does is that silver nitrate, it is soluble in most protic solvents. However, when the silver makes the silver halide, so silver fluoride, chloride, bromide, iodide, it's a solid, so it drops the halide out of solution, so it helps to drive it forward. Anyways, we make the carbocation. Then when the carbocation is made, our solvent, the R and then alcohol, a pair of the electrons on that oxygen goes and attacks the positively charged carbon, right? So this makes this intermediate, right? So the carbon is positively charged, and then the electrons from the oxygen attack it because the electrons are negatively charged. They attack the carbon positively charged center. It makes a bond, and then a positive thing gets attacked by a neutral, or a positive species gets attacked by a neutral species in charge. It will not result in a neutrally or uncharged intermediate. It will result in a positively charged intermediate. What I mean by that is that if you have a positively charged something and gets attacked by a neutral thing, it will result in a positively charged intermediate. So to get rid of that positive charge, what happens in the reaction is that these electrons that are bonded to the hydrogen gets kicked out. The electrons, they find it to be more favorable if there are lone pairs and not positively charged species. So the electrons go from being bonded with the hydrogen gets kicked out, and it leaves as a H plus ion in the solution, right? And then finally, we get our product. Voila. So what happens overall, here, let me put it back. So what happens in this reaction is that the solvent is actually part of the reaction. So if we use ethanol, methanol, and alcohol, or water, it's going to be part of that reaction. Our product, because we have, here, let me push it up. Because we have a carbocation, the carbocation species is actually flat. It's sp1p2. It's sp2 hybridized, which means that in geometry it's actually flat. So it stays still like that. And when the oxygen hits it, so I'm gonna try to demonstrate. So imagine my hand being the carbocation. When the oxygen from the alcohol hits it hits it either from the front, or here I twist the carbocation, or it hits it from the back. So our product is actually going to be racemic both with R and S. So we're going to make both of them if the placement of the OH is a chiral center. Okay, now let's do an example really quickly. So we have 1, 2, 3, so methyl, ethyl, propyl, then 1, 2, 1, 2, so 2 chloro propane, right? And it's this is actually achiral, so let's make it chiral. Okay. So now we have 1, 2, 3, 4. So we have methyl, ethyl, propyl, and then bute, and then 1, 2. So 2 chlorobutane, where the Cl is actually 1, 2. So we go this direction. So it's R. So this is R, right? And we have Cl, and let's react it with some good old-fashioned water. And let's put the catalyst. The catalyst is not necessarily, but you sometimes see it on exams. So let's do this reaction and show all the mechanisms. So first, the Cl gets kicked off. We get this positively charged intermediate, and then the electrons from our solvent H2O attack the carbocation, right? Just imagine we're attacking the carbon, right? And it'll make this product. Okay, we make this hydronium, I guess, intermediate. And then because this is unstable, the oxygen wants to be electronegative and wants to be either negatively charged or neutral, and absolutely not positive. The electrons will find that electrons that are bonded to one of the hydrogens, they'll find it to be more favorable or better for them. They stay as lone pairs and not bonded to the hydrogen. So they get kicked out as hydrogen gets kicked out as H plus in solution. So your solution is going to be slightly acidic, and you're gonna get methyl, ethyl, propyl, and then butyl. So you're gonna get 2 butanol, both R and S, because the carbocation intermediate is flat, so it's gonna hit from both the back and the front. So we're gonna get a racemic mix. Cool. All right. Now let me show you carbocation stability. Now let's talk about carbocation stability. So the most stable carbocation that can we form is third degree carbocation, where the carbon has 3 other carbons attached to it, and then the second least stable is second degree carbocation, which has 2 carbons attached to it, and then it has first degree cation, where only 1 carbon is attached, and then I guess 0th degree, where it's all hydrogens or something other than what do you call it, carbons, right? Okay. What also helps with the stability is that of a carbocation is resonance. If the structure can resonate like that, right, where like this double bond can go flip back and forth between being here and here, it can smear around the charge and make it more stable than if it doesn't resonate. So double bonds, one away from a double bond, is very stable for a carbocation, and it's much more preferred than no resonance. However, structures a carbocation that is charged on the double bond, this is very unstable. This is more unstable than our first right here. So this is, let's write it, unstable. We can notice the same thing with benzylic. This is called, by the way, Lilic. I'm not sure about the spelling, don't judge me. And another fairly stable carbocation is benzylic carbocation. Okay, I'm back. My camera cut off for a sec. Apparently it cuts off every 20 minutes. Anyways, this carbocation is a primary carbocation, but it doesn't have a benzene ring next to it, right? However, this one is primary, right? Or it's your first degree. However, it has a benzene ring next to it. And benzene rings, they are aromatic, so they swish around, if that makes sense, the electrons. They smear the electron charge. So the plus charge could resonate around it, so the electrons could flow around the benzene ring. And it would make this carbocation very stable. So carbocations that are next to benzenes, or benzene rings, or like aromatic rings, they are very stable, and they're called benzylic rings, right? However, same with the allylic, carbocations that are on the benzene ring or on the aromatic rings are fairly unstable. They're like the most unstable out of everything that we just discussed. Same with the allylic carbocation. Also, while my camera cut off, I explained something very important, which is carbocations can rearrange. This means that your structure during its intermediate forms, it could rearrange, and it can change the whole structure of your final compound. So you got to be careful in your mechanisms and make sure you identify that. I'll show you one example right now. Alright, in this example we have methanol. So it's a protic solvent, right? And it's going to be involved in this reaction because it's a protic solvent, and that's the condition that favors Sn1. So our first step is going to be the same. So this is our alkyl halide, right? So this is going to turn into this. Right, so we're going to have this carbocation as our intermediate. However, it's a primary carbocation, right? Though we have a position that can make this carbocation into a tertiary carbocation, or carbocation to third degree, right here. So if this positive charge moved here, it would be very favorable in like the system. So what would happen is that we would have something called, we'd have a hydride shift. What this means is that the hydride is a species that I believe it's charged like this. It's a hydrogen with a lone pair minus. You don't need to know this, but this is just for fun info. The hydride shift, what we'll do is that the bonds on the hydrogen right here, the bonds themselves will be attracted to the positive charge, right? So we'll move the whole hydrogen and the bonds, because we're moving the bonds, or the one bond between the carbon and the hydrogen itself will move too. So this will rearrange. This is a positive charge, by the way. I just messed up the drawing. Notice how I turned it from a wedge to a flat line? That's because, as I mentioned earlier, carbocations are flat. So they can't be, they can't go in and out of the page or in and out of a surface because they're flat. They're sp1, p2, sp2 hybridized. When we have this species, now our protic solvent is going to be involved in the reaction where the lone pair, one of the lone pairs, is going to go and then hit that positive charge. It'll actually hit the carbon, not the positive charge, because, you know, there's no physical positive charge. It's more of, it's going to hit the carbon. It's not going to hit the positive charge. Because, like, you get what I mean. It's going to hit the carbon atom itself. Let me just redraw it. Like that. So it's going to hit the carbon itself because the carbon is positively charged. There's no such thing as a physical charge that's floating around. It's the carbon that's positively charged. And we're going to make a racemic, both R and S, of, we're going to make this product right here, both R and S. That means that this methyl could be going backwards or forwards, and this one could be going backwards or forwards. In other words, we're going to make these two. So we can have one species that's going backwards, so the OCH3 is going backwards, and one's going, I drew both of them. I drew the same compound twice. Great. Well, I guess it's not, but I just drew it in a confusing way. So like that, right? Both R and S. Some of this species is not gonna rearrange, and some of it is just gonna get attacked by the solvent, the protic solvent. So some will just turn into this. So some of it will turn into this compound, or redrawn would be that, right? So this is our CH3, because the solvent attacked this thing first. So you can have some of this product and some of this product. However, the major product, or the majority of your product, is going to be this one. So it's going to be something like 70% this, and then 30% that, right? Alright, I'm back. I ran out of my nice clean white paper, so now I'm reverting back to my line paper. However, I'm gonna still use the Sharpie. Let's do another example. So I think this is example numero 3. Okay, so now we have this example, right? So we have this reactant, and it's reacting with ETOH, or in other words, ET is used as abbreviation for ethyl. So ethyl OH, ethyl alcohol, ethanol, right? So reacting it ethanol. Ethanol is a protic solvent, which contains usually an OH group, so like water, ethanol, methanol, butanol, etc. We want to know what's the major product. So, yeah. Let's start with taking out this Cl, this chloride out, converting it into carbocation, because that's what happens in the reaction. Okay, so right here we have carbocation that's on the secondary position, right? Or the second degree. It's a second degree carbocation. However, next to it there's a benzylic and a tertiary carbocation, or carbocation to a third degree. This means that this product, this carbocation, is gonna rearrange. And it's going to rearrange by taking the hydrogen that's popping forward and doing a hydride shift, right? And we're going to form this. Okay, so now we have two species. One that's carbocation that's not rearranged. However, it's not benzylic or tertiary. This one is tertiary and benzylic. So our major product is going to come from this rearrangement. Now, let's do... So now the oxygen from the ethanol is going to attack the carbocation. It's going to make this species. So I'm going to draw the intermediate. Right, so we're going to make this species. And it's going to be positively charged, and then the hydrogen is just going to go away in solution, and then we make this product. Alright, I'd like to correct myself. Right here, this should not be hydrogen, this should be an ethanol, an ET. I know it's kind of muji right now, but this is an ET, so this is CH2 and then CH3. So carbon, carbon, two carbons, ethyl, so like ethane, etc. Yeah, so the hydrogen will still gets kicked out, and then we're gonna get this species as our final product. This is gonna be both, so this chiral center is gonna be both R and S racemic. So we're gonna get both the R and the S almost equivalently. Now right here we're gonna do the same thing, so we're just envisioning not envisioning but part or a proportion of the unrearranged intermediate is gonna react with our solvent, and it's gonna make an ester. So it's gonna proceed with the Sn1 without rearrangement, but it's gonna be the minor product. So this is gonna be okay, so we're gonna get some of this. Notice how right here we don't have this as going backwards, but this right here in unrearranged, we have it going backwards. This is because the carbocation is a flat molecule. So the OH and the ethanol can hit it from the back or the front. So we get racemic, both R's and S's. Right here, it never becomes a carbocation, so that ethyl subgroup will stay in the back, so we'll have the dashes. Right here, I did the squiggly line. This is a notation indicating that we both have R's and S's in this compound. Let's do one final example. Alright, I'm back. For those who are observant, I switched my paper with a lower quality paper. See, it's like ripped from a notebook. I actually ran out of line paper. So yeah, I'm running out of paper. Kind of sad. Anyways, apologies for the quality degradation in my writing paper. This final example is interesting because it has a little twist. Two twists. One is that we're using D2O. If you look at the periodic table, D is not an element. It's actually a shorthand for an isotope of H, or hydrogen. It's a heavier isotope of hydrogen, and it's called deuterium. It has one extra neutron, because usually hydrogen doesn't have neutrons, if I remember correctly, and deuterium has one extra neutron. So it's a heavier element, pretty much, or not element, excuse me, but a heavier isotope. So we can treat this pretty much as same thing as hydrogen. So this is H2O, but with a isotope of H, or D2O, or heavy water, I think it's called. We're using the catalyst AgNO3. I showed it in previous example. Anyways, let's do this. This is an interesting example because it has a twist. So first, let's write the carbocation intermediate. So we have this molecule right now, and this carbocation is a second degree carbocation because it's attached to two carbons. Or this carbon, the carbon that's positively charged, is attached to two carbons. Next door, there's a very favorable position that has more carbons than two. However, it has 4 carbons. It has no hydrogens for it to do a hydride shift. So what it does instead is it shifts the electrons from the ethyl onto the carbocation carbon. So what happens is that when you shift the electrons that are bounded to the ethyl or to the methyl, you do something called a methyl shift. So you'd get this intermediate. So what happened is that the methyl moved from being bounded here, and then it moved to the carbocation carbon, or the carbon that's positively attached. So what it did is that it moved the whole methyl group onto where the carbocation was, because if you notice, we now have a very favorable tertiary carbocation, or carbocation to the 3rd degree, or a carbocation that's attached where the carbon is attached to 3 other carbons. Now we can do Sn1, or the oxygen. We can attack with the oxygen on both the unrearranged and the rearranged. However, the rearranged is going to be the major product. So now we have the hydronium kind of ish species, where it's like the water and then it has a positive charge. Then the deuterium is going to get kicked out. Just pretend it's hydrogen because it acts the same way. And then we get this molecule as our final product, both R and S, so racemic. And for this one, we can do the same thing. Now, this molecule is going to be our major Sn1 product. Alright, now we have these 2 products as our products of this reaction. Now, I'm gonna hit on a couple of notes before I leave. Alright, I'm back. For those who are observant, again, the quality of the paper has degraded. This time was just out of laziness and to continue with the theme of quality degradation. Just a couple of notes is that the reaction, this is an X, not an R, so carbon attached to a halide, and then plus R dash, and then our product, what makes our product solvent, so the ethyl group, or not the ethyl group, but like the alcohol group, the OH. Now, the rate law is, so this is our rate law for this reaction. What this means is that the speed of the reaction, or the rate of it, is only dependent on the alkyl halide, or exactly the step where the electrons go from the bond between the carbon and the halide to the halide, where it gets kicked off as an ion in the solution, and it makes the carbocation, the carbon plus, right? So this step is the slow step, and it's the rate determining step. What this all jaboggle mean is that the concentration, what affects the rate is only the concentration of the alkyl halide. So if we have, let's say we have a reaction of this plus let's say H2O, right? So we have methyl ethyl propyl, so 2 chloropropane and water, and let's say we double the concentration of the 2 chloropropane, and if we double the concentration of the 2 chloropropane, our rate will double. However, if we double the reaction of our water, which is part of the reaction, the rate will not change. Reasoning is that the rate is dependent on the alkyl halide. Same thing with the opposite. If we decrease the concentration of 2 chloropropane, the rate will decrease. So if we decrease it by half, it will decrease by half. Or if we double it by 2, it gets doubled, right? However, if we also decrease the concentration of water, the rate will not decrease. Alright, I think that's all I have for you guys today. Thank you for watching. I'll probably have posted some practice problems, probably not mine, on my description. So check out my description. And yeah, thank you guys for watching.